All right. I think I'm one of the only NLP people in the room that we'll be hearing from Ellie later today, perhaps the other of us. So for those of you who are interested in deep learning but have not worked on natural language processing, natural language understanding, let me just give a little bit of context about the last 2 years. We probably won't be very surprised to hear that the introduction of deep learning methods into NLP has had a huge impact on what NLP research looks like and a pretty substantial impact on sort of practice in applications in the field. To give some examples of this, looking at reading comprehension. This is a task that's been introduced to NLP relatively recently, where a system is asked to read a paragraph and answer a few short questions. Maybe this might resemble something like the language sections of the GRE. Here, this sort of when this was introduced a few years ago, this seemed like a kind of very straightforwardly difficult language understanding test, and as of just a few months ago, we've now reached human performance. The systems that we have are quite brittle. I think it's reasonable to say that they're not doing language understanding in any generalizable way, but this is nonetheless a pretty major milestone. In translation, we're nowhere near human performance, but the introduction of deep learning methods into translation has yielded pretty dramatic, sort of qualitatively obvious improvements to the kinds of translations we're able to produce, at least for language pairs like English-French, English-German, where data is really abundant. And then syntactic parsing is an interesting case. This is the task of reading a sentence and assigning some structure to it, saying sort of what modifies what substrings of the sentence are kind of meaningful phrases. This is a task where we've had, the NLP community has agreed on a single test set for this task for the last 25 years, and a tremendous amount of work has gone into sort of optimizing systems for this one test set. And it really seemed like we'd kind of optimized it to death, and progress had slowed, and the introduction of deep learning techniques into parsing has kind of reignited a bit more progress in this direction. So things are moving quickly, and we're getting big gains on at least some of the tasks that people in NLP really care about. So the question that I'm interested in, and I'm certainly not the only one in the NLP community interested in this, is to what extent are the sorts of deep learning tools that we're already applying to NLP able to do anything that we would recognize as compositional semantics or as kind of principled systematic language understanding? With one of my hats on, I'm a linguist, and so I'm sort of asking, all right, to what extent are these systems able to do the things that we think humans are able to do? And I'm interested in asking this question less about any particular instance of a particular model and a particular task, and more about just the kind of set of technologies that are currently under study. So I think the best way to pursue this, given that, is to pick a task to focus on, and bottom of the slide's cut off. Is to pick a task to focus on and see how far we can go with a task that we think sort of implements this goal. So at the beginning of this talk, I'm gonna sort of make the case for the task of natural language inference as a kind of research benchmark for work on systematic language understanding with deep learning methods. Here's what the task looks like. It's called Natural Language Inference, NLI. You'll also hear it called Recognizing Textual Entailment, or RTE. It's a sentence pair classification task. So here's an example from Bill McCartney's thesis a few years ago. In an instance of this task, a model will be given two sentences. Like here, James Byron Dean refused to move without blue jeans, and James Dean didn't dance without pants. And the model will be asked to choose from a small fixed set of labels the label that best describes the relationship in somewhat logical terms between the meanings of the two sentences. So here the options are entailment. This means that sort of whenever A is true, B must also be true. That applies here. Alternately, we could have contradiction. In that case, whenever A is true, B must be false, or the sort of neutral or neither case. So this is all the task is. The claim, though, is that if we get a kind of reasonably broad sample of naturally occurring language and use it to construct an NLI data set, then in order for a system to be able to get close to human performance in that data set, it should have to be able to come up with a reasonable account or a reasonable treatment of all of the phenomena that we as linguists think constitute kind of the hard work of language understanding. You'll need to be able to handle word representations and lexical entailment. You'll have to know that any cat must be an animal and no cat can be a dog. You have to deal with quantifiers. This is sort of a classic object of study in logical semantics. You have to know what fewer than 8 means and how to handle scoping there. You have to be able to resolve ambiguities both in word meaning and in sentence structure. You have to be able to deal with modality. This is things like might or should or can. You have to deal with beliefs, things like think or know. You have to bring in background knowledge to do all of this. And I'd really argue that this sort of list goes on and does really include all of the major phenomena that are studied and that we think constitute sort of semantics and systematic sentence understanding. The one caveat here is that this is an ungrounded task. We're studying a model's ability to understand language in isolation. We're not requiring it to build connections with any kind of perceptual reality or any kind of model of the world. This is arguably a disadvantage, but it also allows us to study the technologies as they currently exist, because most of the work that is done in NLP is done in this kind of setting of isolation without a direct connection to some kind of perceptual world. So why not some other task? NLI has the unfortunate property of being relatively useless. Systems for NLI do show up occasionally in real applied pipelines, but not that often. There are lots of NLP tasks out there that are actually useful and will make people money. So why not one of those? On one hand, there's been a good deal of work with this goal in mind, work on building systems that we think are capable of principled systematic language understanding that is focused on tasks that I think are too easy in the relevant sense. These are tasks like sentiment analysis, judging whether a review is positive or negative, and sentence similarity, judging whether two sentences mean similar things in some undefined similarity metric. I think for these tasks, you could argue that they do require sophisticated language understanding in some limit cases, but on typical data sets, you can get to very near human performance on these with relatively simple keyword spotting or keyword matching. So I think these aren't testing the things we'd like to test. On the other hand, there are plenty of tasks that do require sort of real sophisticated language understanding in reasonably typical cases that we might consider. These are things like machine translation or open domain question answering or dialogue systems. And the reason that I'm not advocating for these tasks is that they all require you to do effective language understanding, but they also require you to solve some other as yet unsolved difficult machine learning problem as well. To do translation, you need to be able to understand a sentence, but you also need to be able to map some abstract representation of that sentence back into a new sentence, and that is at least as hard. For open domain question answering, you need to be able to understand a question, but you also need to be able to learn, presumably in end-to-end fashion, to go out and search for relevant information, and that's still something that we've not yet solved. So NLI, as a simple balanced classification task, is dramatically easier than all of these in everything except its requirement for principled language understanding. So on to the rest of the talk. That was sort of the preamble. The majority of this talk is going to be organized around a couple of sort of benchmark data sets that I put together and the results we've seen on those. And then toward the end, I'll talk a little bit about some ongoing work that I think would be interesting discussion for sort of interesting fodder for discussion in this room over the next few days. So the first project is some work that I did a few years ago at Stanford with these lovely co-authors. And this was a data collection project. And so I started working on NLI in 2014. And as of then, this was the layout of data sets we had. There were 3 data sets that were the kind of data that we wanted, but almost certainly too small to train a language understanding system in a purely supervised setting. The largest of these had about 10,000 examples. Half of that was a test set. On the other hand, we had 3 data sets that were reasonably large, but that were collected using automatic sort of heuristic methods and turned out to be biased in pretty severe ways. I threw a year or so of my life at trying to find ways to combine these and also to use unlabeled data to get a working NLI system, and nothing worked. And I'm not alone. There was actually a large NLP shared task competition on natural language inference with neural networks, and no one really got it to work. There were quite a few teams that submitted, but none of the top 10 teams actually used neural networks. So we went out and collected the data that we thought we needed. We got a grant and threw it all into Mechanical Turk and collected a little over 500,000 examples of this kind of data. Here's where it comes from. This is what we showed to annotators on Mechanical Turk. It's a little blurry. I'll read it. We will show you the caption for a photo. We will not show you the photo. Using only the caption and what you know about the world, write one alternate caption that is definitely a true description of this photo, write one that might be a true description of the photo, and write one that is definitely a false description of the photo. We then give them a real description of a real photo in blue. We throw out the photo. And then we have them fill in 3 text boxes, here, here, and here. When they fill in the first text box, they're giving us a sentence that is entailed by the premise sentence in blue. When they fill in the second, they're giving us one that's neutral with respect to the premise in blue. And when they fill out the third, they're giving us a sentence that that contradicts the premise sentence in blue. So for each of these, we get 3 labeled pairs. After sort of quite a bit of going back and forth with our annotators to try to figure out exactly what examples to give and exactly how to word this, we think it more or less got at the phenomena we were interested in. So here are some examples. These are random samples. They're by far not the best in the corpus, but I think they give you a sense of what it looks like. 2 women are embracing while holding to-go packages. 2 women are holding packages. Entailment. Boring but reasonable. A man in a blue shirt is standing in front of a garage-like structure painted with geometric designs. A man is repainting a garage. Neutral. Reasonable. A man selling donuts to a customer during a world exhibition event held in the city of Angeles. A woman drinks her coffee in a small cafe. Contradiction. This is actually exactly the kind of thing we want for a contradiction in NLI. There are good reasons for this that I can talk about offline. We define 2 sentences as contradicting one another if they cannot be true of the same event or the same situation in an event semantic sense. So these 2 sentences could both be true and they could both describe things that are taking place at roughly the same time and place, but they can't describe the same event with the same participants. So this is exactly what we want as a contradiction. So let's do some machine learning, see if we can actually get our systems to learn this kind of reasoning. First, some baselines. If we just guess randomly, we've got to get about a third of this right. It's more or less balanced classification, even after some filtering. If we build a big localized classifier that's meant to represent kind of the best we can do without any kind of particularly sophisticated learning, without anything that we think we'd recognize as language understanding, we're able to do pretty well. And this is a powerful model. This has a lot of fairly carefully crafted features, and about 1 million features. It gets it to about 78%. On to neural network models. Throughout the rest of this talk, I'll be distinguishing between 2 rough classes of models. Sentence encoder models are these Siamese networks in which you have a distinct component of the network that reads each sentence and maps it to some kind of fixed size representation, the sentence encoder. You apply this to each of your 2 sentences, feed those into something like an MLP that combines them, and then predict the class. This is sort of the natural thing to do if you really are thinking about NLI as a problem of testing a model's ability to do sentence understanding. On the other hand, if you want to optimize for performance in the task, you'll probably wind up using attention or memory methods to look at alignments between words and phrases in the 2 sentences. That turns out to be a very useful tool in this kind of tasks. So here we might have encoders that don't have any kind of fixed size bottleneck and that communicate with each other and with some additional components using methods like attention and memory. So we put this task. So here are some sentence encoding baselines. If we just use kind of simple standard techniques, if we represent a sentence as a sum of word embeddings, a sum of word vectors, we get about 80 or 81% accuracy. If we switch to bidirectional LSTMs, we get a little bit higher than that, but not much. We put this online in the middle of 2015, and I think we succeeded in getting this to take off as a major evaluation task in NLP. We've gotten around 100 systems built for this task. So here's the state of the art as of now. Looking at sentence encoding-based models that represent sentences as kind of fixed size representations, the best that we've seen is a model that gets about 86% accuracy. It uses attention, but only within each sentence. And then the overall state of the art is about 89%, and this is a model that uses attention across sentences, attention between sentences, ensembling, a few additional tricks, but nothing too surprising to anyone who works on NLP. So what should we make of this? We're not at human performance yet. That would be at least the mid-90s. But this is kind of we're seeing kind of reassuring results after all of these published results. We've seen people try many kinds of feature, many kinds of model, many kinds of outside resource, and the systems that do best generally don't stray very far from kind of the standard deep learning toolkit as it exists for NLP. Most of these systems are using some combination of LSTMs, attention, pre-trained word embeddings, maybe ensembling. So our systems are doing reasonably well. They seem to be able to capture at least some parts of language understanding. that, I'll move on to a follow-up project. This is work that I did more recently at NYU with a couple of grad students, Adina Williams and Nikita Nangia. And the motivation for this project is that sort of, well, I think SNLI succeeded in kind of launching this task. It's got some pretty serious limitations. There's not that much headroom left. And I think what remains in this 6 or 7% of headroom is largely involves things like sort of common sense knowledge, intuitive physical reasoning, intuitive social reasoning that is actually going to require skills far beyond what we'd expect to see in a pure language understanding system. So I think kind of getting this last bit of headroom is going to require going far beyond NLP. And more importantly, SNLI didn't really fulfill the kind of promissory note that I gave you in the beginning of the talk. It doesn't require a system to kind of grapple with all of the phenomena that you'd expect to see in English. There are things like reasoning about tense and timelines, reasoning about beliefs and knowledge states, reasoning about modals, things like should or could and permission. These phenomena show up almost never in language that is talking about a concrete visual scene, and that's what SNLI is. So we'd like to find a data set that really captures kind of the full diversity of ways that you'd use natural language. So with that in mind, we went back to Mechanical Turk, or a Mechanical Turk competitor, and collected some more data. Here, instead of working in this sort of constrained, relatively easy genre of captions, we drew 5 different sources of source text from the Open American National Corpus. This is a pre-existing data set that's meant to capture kind of a representative sample of American English. We got kind of 5 sections of this from the 13 or so sections the corpus is built out of. We got kind of lowish brow fiction, government publications, magazine articles from Slate, transcribed telephone calls, and travel guides. We also went back and sampled 5 more genres from this kind of broader corpus for which we collected only test and development sets. So what we wound up with was a corpus of a little over 400,000 examples that's ideally meant to cover kind of the full range of American English. And the hope is that if you're interested in kind of focusing on the conventional machine learning use case where you expect your test set to be distributed in a very similar way to your development set, you focus on this first evaluation set. If you really want to be able to claim that your system is sort of fully understanding American English, you'd hope to focus more on this kind of different sample of genres, this different sample of data sets. Here's what this data set looks like. Hopefully you'll notice a difference with SNLI. In contrast, suppliers that have continued to innovate and expand their use of the 4 practices as well as other activities described in previous chapters keep outperforming the industry as a whole. The suppliers that continue to innovate in their use of the 4 practices consistently underperformed the industry. Contradiction. This is a straightforward contradiction, but you have to keep track of a reasonably richly structured sentence in order to be able to detect that. This example is from Switchboard, transcribed telephone calls. For those of you who have not worked with transcribed speech, in conversations, people tend not to actually use anything we'd recognize as a nicely delineated sentence, and this is amplified in telephone calls when timing and interruptions become difficult. So this is normal-looking telephone speech. Someone else noticed it, and I said, well, I guess that's true, and it was somewhat melodious. In other words, it wasn't just, it was really funny. No one noticed, and it wasn't funny at all. Contradiction. Cool. So this is going to require somewhat different methods than we'd expect to need for SNLI, I hope. The father can beget new offspring safe from Macbeth's hand. The son is the palpable threat. The son wants to kill and to marry his mom. Neutral. All right, so I think the data does look somewhat more diverse than what we'd had before. And looking at some numbers, it does seem like we were able to create a data set that was considerably more difficult. Looking at inter-annotator agreement measures, the 2 data sets are pretty much identical. This is not hard for humans. But if we take the state-of-the-art systems from SNLI and we retrain them and retune them with public implementations on this new data, their performance tends to fall by about 15 percentage points. So this system is dramatically harder for the kinds of tools that we're used to using for this task, which is reassuring. And it seems like this data set is more difficult for the reasons that we're hoping it would be. If we look at the incidence of these phenomena that we've been talking about, they all show up quite a bit more. Sort of modals, these things like kind of might and should and could, go from absent to showing up almost a third of the time. Negation goes from rare to reasonably frequent. Words describing belief go from absent to about 20% of the data set. So this sort of has a pretty good representation of all of these things we think constitute semantics. This has been up for about 6 months, looking at some early results. People have been able to get a little bit higher than where we started, but still we're not particularly close to human performance. With pure sentence encoders, we're getting around 75% accuracy. With models that use attention and some clever applications of convolution, we're able to get up to about 80%. And one reassuring note is that the difference in performance between the matched and mismatched sections of the test set, between the kind of in-domain and out-of-domain performance, is actually quite small. It seems like the sort of tools that we have, when given a diverse enough training set, are able to generalize outside that training set relatively easily. One exciting sort of side result that came out of this project, and this is due to Alexei Kano et al. At Facebook AI Research Paris, and a follow-up paper by Subramanian et al. At Mila, is this work on pre-training with NLI. And I think the crucial result is cut off here. But if you train a sentence encoding model, something like a bidirectional LSTM, on these two NLI data sets, that will get you actually pretty good representations of sentence meaning. And the way that we evaluate this, and I think this is a strange evaluation, but it's become the standard, is you try to solve a variety of language understanding tasks using only logistic regression models trained on your sentence representations. And at least by this metric, representations trained with NLI are almost certainly the best we have. So it seems like this task is forcing models to learn reasonably useful semantic features. So let me wrap up on NLI and then quickly move on to this kind of follow-up project. So NLI lets you judge the degree to which models can learn to understand natural language sentences in a reasonably direct way. With SNLI, it became possible for the first time to train low-bias machine learning models like neural networks on this task and this benchmark. Multi-NLI makes it possible to test models' ability to understand American English in pretty much its full range of uses and phenomena. And sentence encoding functions trained on data like this are quite possibly the best general-purpose sentence understanding tools we have. So onto a somewhat related project, and this is joint work with Adina Williams again and another NYU graduate student, Andrew. The goal of this project is learning syntax from semantics, and I'll get to how this ties in. So the idea here is we'd like to take a task like NLI that tells a model something about what a sentence means, and see if we can use just that kind of data and that kind of task setting to learn something about the structure of the sentences, to see if we can learn to parse sentences to identify what modifies what are sort of coherent phrases. And a sort of important piece of background for this is the success, or at least existence, of a family of models called recursive neural networks, or in the sort of more modern form, TreeLSTMs, or TreeLSTM RNNs. These are sentence encoder functions. They map from a sequence of words to a single vector. And they do this by replacing the kind of linear sequence that you see in a conventional RNN, like an LSTM, with a binary branching tree structure, where that binary branching tree structure comes from a conventional NLP parser. So we have some pre-trained tool trained on a data set like the Penn Tree Bank that gives us this structure. And we apply something that looks a lot like the LSTM layer function, but takes two equivalent inputs. We apply that recursively up the tree to get our sentence representation. These have been around for 6 or 7 years, and what we've discovered consistently through that time is that TreeLSTMs outperform comparable sort of sequence-based LSTMs by small margins on tasks like sentiment analysis or translation or NLI that seem to require some language understanding. And these margins are not always big enough to be worth it. They might be 1 percentage point, and these models can be quite a bit more difficult to implement efficiently, but this is kind of the crucial fact motivating the rest of this project. What we'd like to be able to do is build a single model that we can sort of train as one model that both can learn to parse sentences, can learn to assign tree structures to sentences, and can then use those parses in something like a TreeLSTM to derive sentence-level features, and then use those features to do a sentence understanding task like NLI. Then we'd like to train that entire model, including the parser, only on a standard objective function for NLI data like SNLI or multi-NLI. So essentially, we're training a model that has this big binary tree-valued latent variable in it. A couple of reasons why we might want to do this. From an engineering perspective, seeing what kinds of tree structure we discover might tell us something about how we should build our parsers, how we should build our parsing formalisms to better solve the problems we have. On the scientific side, I think this is somewhat more important. A lot of arguments in linguistics and cognitive science concern the degree to which a sort of low-bias learner can learn to identify the correct kinds of structure in can learn to identify the correct kinds of structure in natural language sentences. So I think there's quite a few scientific problems that this kind of work could bear on. So we were not the first ones to think of this problem. Over the last years, we've been working on this. 3 papers have come out, two from DeepMind. All 3 of these use TreeLSTMs and SNLI, and all 3 of them report this kind of fundamentally successful result. They find that a model trained in this way does better if it's discovering its own trees than if you give it trees from an external parser and train it in that way. So it seems like these models are discovering trees that are somehow better suited to the task than the ones we'd previously been using. And all 3 of these models use different ways to kind of deal with this tree-valued latent variable. This Yogatam paper from DeepMind uses a shift-reduce parsing algorithm and the reinforce rule to train it. Another DeepMind paper uses a chart parsing algorithm and a sort of soft gating, soft relaxation with backprop. And then this Choi et al. Paper with by far the best results from Seoul National University uses a somewhat novel parsing algorithm derived from some of King-Hyun Cho's work, combined with the straight-through estimator and Gumbel softmax. But none of these 3 papers has actually really kind of shown you what the resulting grammar is. They haven't really shown us what these trees look like. And so we wanted to take a look at that. We reproduced these results, and we got a somewhat disappointing outcome. If we optimize these systems strictly for development set performance, we're able to get numbers that are at least as good as what we were seeing. But all of these systems seem to be learning fairly trivial strategies. You can only really see one of these, but the models that use shift-reduce parsing tend to learn these structures that always branch in the same direction. You always build the kind of leftmost constituent you can build. And so you wind up with this tree that is almost equivalent to what you get with a plain sequential RNN. And this kind of parsing strategy doesn't meaningfully depend on the input. With some of the other parsing algorithms, you'll wind up getting tree structures that are as balanced as possible, that are sort of to the extent that you can get this with arbitrary number of input words, you get these maximally shallow, maximally balanced trees. And when you have to break some kind of tie to meet that goal, you'll break it more or less arbitrarily or randomly. So it doesn't seem like these models have yet learned to identify anything that we would think of as kind of structure in language in the sense of something that is reasonably systematic and that varies as you change what the input sentence is. We're not there yet. There are a couple of reasons I think this fundamentally remains a very difficult open problem. First, it's this kind of premise that the gain in performance you get by switching from a completely arbitrary parsing strategy to what we think of as a plausibly pretty good parsing strategy that we've seen in earlier work on TreeLSTMs is quite small. It might be a 1% absolute performance gain. And it's seeming like strategies like coming up with these kind of strictly balanced trees get you pretty close to that performance gain. So the kind of last remaining margin in final task performance you get by doing the right thing is extremely small. And doing this kind of discrete optimization in that setting is quite difficult. I think there's some room to make this easier by just finding ways to better exploit tree structure and make that margin a little bit larger, a little bit easier to detect. More importantly, and a little bit more fundamentally, I think this problem requires what seems like a very difficult kind of search. We're not trying to find the parsing strategy that is optimal with respect to some fixed neural network sentence understanding component. We're searching the sort of cross product of all possible parameter sets for our relatively large neural network with several million parameters, and all of the possible parameter settings of our parser. And the trouble is, as you sort of consider a new possible strategy for your parser, you might need to wait tens or hundreds or thousands of gradient updates for the neural network to kind of catch up and learn to exploit that new behavior. And doing exploration in this kind of setting seems fundamentally difficult. I'd love to chat with anyone who has ideas on how you might do optimization in this setting. So with that, I'll wrap up. If you know anyone who's hiring in a linguistics or cognitive science department, Adina is on the job market. Nikita and Andrew are both applying for PhDs, and look forward to spending the week here.